Part 3, modeling with quadratics. Now, modeling quadratics is basically when you have a situation where you have data or information, and the data, instead of just going straight up, starts to do this. Well, it's going up and then it goes down. It's going like that. It can't be a line, because lines only go in one direction. Either you have a line that's going up or you have a line that's going down, right? And if you draw a line, it's just growing, but this is not growing. You can try to say it's a curve, but here's the problem with a curve. When you do a curve like this, the curve will still be growing because exponential curves keep going in one direction. So this is only modeled with a quadratic. It goes up and then it goes down, like a U shape. Now, there is one very popular one, or one that's very commonly used in physics, and this is called the vertical motion model. Okay, let me write that down. This is the vertical motion model. Let me explain what it is. All right, now when you throw an object or an object falls, gravity, which is represented here by -16, pushes it down at an acceleration. So that acceleration is how fast the object is being pulled to the earth. Okay, here, this is the velocity when the object started. How fast was it going at the beginning? Because it's going to change over time. And that's what t is. T is time. The last thing is the initial height. So we have gravity, which is represented by 16. We have the velocity, which you have to find out of the object, and the height at the beginning. And they're usually called the initial velocity and the initial height. So we have to find these things when we're going to use this model to predict the height over the time. So that's what we would expect to see with this kind of model. It goes up, then comes down, right? So, for example, if you drop a ball from 10 feet at an initial velocity of 2 feet per second, your function would look like this. That's it. And if you kick a ball and it's going 9 feet per second, and the initial height was 1 foot, your function would look like this. Okay, so that's how you basically write your function down. That's basically it. And sorry, I misspelled height, so I had to erase that. Now, if you're going to graph it, you're going to do the same thing you did before. Find the vertex, negative b over 2a, and put that in the middle of your table. So in this case, if I do negative 2 over 2 negative 16, I would get 1/16th, and that decimal would be something like 0.0, take your calculator out, 1 divided by 16, 625. Okay, that is where your vertex is going to be. You graph that, that'll be the highest point of your graph. Now, wait, would it be negative? Let me do that. Negative b over 2a. Yeah, that would be it. So, if you actually did a graph for this, you're going to notice it's so close to 0 because this is a ball that is just falling. It's just a ball that's falling. Wait a minute, where's the rest of the parabola? The rest of the parabola would be over here, but there's a problem. Guys, if this is t, you cannot use -1, -2, -3 because that would be negative time. There is no negative time. So you're not using this side of the graph. In your model, you're only using from 0, from right now, to the future. How much time forward as this object falls. And it'll graph me the location of the distance that it's falling at over time. So you have half a parabola here. Okay, if you did it on this one, right? -9 over to negative 16, you're going to get something like 0.3 or something. I'm rounding it, just trying to save some time. And this model would show you kick a ball, goes up quickly, but then falls very quickly as well. And again, you wouldn't use negative down here either, because once the ball hits the ground, it might bounce a couple times, but it's going to stay basically where it is. The curve, if you keep extending it down here, what you're saying is the ball's going underground, because now you're using negative distance, -1, -2, -3, and this would not be time. Remember, time is this axis, this is height. That would mean that the ball's going into the ground, and you must have kicked it really hard to do that. So that's not going to be used. So you don't use this part of it either. Again, you're going to stick with the positive side. So modeling can be tricky because you have to understand which parts make sense and which parts are practical. All right. A last example to model is, let's say you're designing something, a rectangular garden, okay, with a 2-foot wide path all the way around it. What is the length of the garden? Is 3 times as long. Okay, so let's say you have a rectangular garden. I'm going to try to draw this as best I can. Let me push this down a little bit. Okay. So we have a rectangular garden, right? And it has a path alongside it that's 2 feet in all directions. 2 feet, 2 feet, 2 feet, okay? And then it says that the length of the garden is 3 times as long as the width. So if this is the width, and let's just say it's x, and this is 3 times as big as the length, sorry, 3 times the length, yeah. So it's going to be 3x. So let me clarify that because I read that weird. It is 3 times longer than it is wider. The length is 3 times as long as the width. I think I didn't put that in the model, so I apologize for that. But guys, this would be my model. This would be the example of the garden. Now, to multiply to get the area, I need to multiply this side times this side. So that means from here to here, I'm using 3 different dimensions because this is x, but then I also have 2 feet and 2 feet of walkway, which makes this x plus 4. This is 3x, just the garden, but it has a walkway of 2 feet this way and 2 feet that way, which would make this 3x plus 4. So if I took those lengths and widths to find the area, length times width would be x plus 4 times 3x plus 4. So I would have to multiply that. You would have to multiply that to get the area. And we've already talked about this. You would want to use the area model to multiply that. Okay? Okay, so these are some examples where you would use quadratics to model. Okay? And the reason this is a quadratic, because when you multiply this, you're going to get 3x squared. X squared is your quadratic.